very much. In a lecture at Cornell University in 1964, the physicist Richard Feynman defined the scientific method. First, you guess, he said to a ripple of laughter. Then you compute the consequences of your guesses. Then you compare those consequences with the evidence from observation or experiments. If your guess disagrees with experiment, it's wrong. And that simple statement is the key to science. It does not make a difference how beautiful your guess is, how smart you are, who made the guess, or what their names are. It's wrong. Matt Ridley of the Wall Street Journal wrote an essay in October of 2020 entitled, "What the Pandemic Has Taught Us About Science." If you haven't seen it, it's a great read. In his essay, Mr. Ridley reminds us of Richard Feynman's lecture and encourages us to think of science as a game of guess and test. He notes that the COVID-19 pandemic has stretched the bond between the public and the scientific profession as never before. He writes that scientists have been revealed to be neither omniscient demigods whose opinions automatically outweigh all political disagreement, nor unscrupulous fraudsters pursuing a political agenda under a cloak of impartiality. Somewhere between the two lies the truth. Before giving numerous examples of the scientific hits and misses during the pandemic, Mr. Ridley states, science is a flawed and all too human affair, but it can generate timeless truths and reliable practical guidance in a way that other approaches cannot. Science is not about pronouncing with certainty the known facts of the world. Rather, it is about exploring the unknown by testing guesses, some of which will eventually prove to be wrong. Aquifer science does not seem to be quite as controversial as the science surrounding the pandemic, but still, I find it useful to think of science as a game of guess and test. Today, I would like to highlight a district that is doing some wonderful science here in Central Texas. The Clearwater Underground Water Conservation District has hired a group of scientists to learn more about their aquifer systems. Each of us has different areas of specialization, and we have been working closely together in order for the district to benefit from our collaborative efforts. Before I get to my own work, I'd like to show some of the earlier work done by a few of my colleagues. Mike Keister of LRE Water has been studying water level declines in Bell County for several years now. I am borrowing this figure from one of his publications. When collecting water level data and plotting water level declines between the years of 2006 and 2018, Mike noticed two significant cones of depression. One is located near the southern part of Bell County in the Hidden Springs area. The other is in Williamson County in the Sun City area. This led many of us to guess why this is happening. For example, could it be new wells and more pumping near Hidden Springs? Could it be because of development in Williamson County contributing to the regional drawdowns? Or could it be because of heavy regional use of the Trinity Aquifer in areas north of Bell County? Could there be more than one cause of drawdown? Alan Standen and Vince Claus of Alan R. Standen, LLC, had another guess. Perhaps they thought, this has something to do with the underlying geology. We already knew that the aquifer was thin and close to the surface in the southwest part of Bell County. Alan and Vince hypothesized that the fault structure in this area may be causing compartmentalization of the flow system. So how might this work? Well, we know that faults can act as either flow conduits or flow barriers. This illustration I borrowed from ResearchGate illustrates how this can happen. If the offset between two fault blocks is large enough, it would prevent groundwater flow from one block to another because the water would encounter a less permeable unit. Or the structure may create relay ramps, as it does in other parts of the Balcones fault zone, which will transmit water down the ramps. A third possibility is that during the fracturing of the rock, The fault can form with a low permeability core surrounded by highly permeable fracture zones, therefore complicating the groundwater flow path. To test this guess, Alan and Vince proposed to collect drillers' reports and geophysical logs to map the top of the Middle Trinity Aquifer with high detail in southern Bell County. This next series of slides shows the progression of their work. In the first slide, we see the study area. The county line between Bell County and Williamson County is near the bottom third of the figure. The points show the location and number of wells that were used to define the top and base of the Middle Trinity Aquifer. The red wells show data collected in previous years, and the green wells are wells that were added in 2020. This gives you an idea of the data density. This next figure shows the elevation at each well point on the top of the Middle Trinity Aquifer. Vince interpreted the aquifer formation surface using interpolation tools in GIS. The color gradient represents changes in elevation. He also sketched out preliminary ideas of where some of these fault blocks may be occurring based on this elevation data. If there is a significant change in elevation between 2 points that are near each other, a fault may be present. Vince was looking for vertical offsets of around 50 feet or more. I find the next figure quite intriguing. Vince plotted gallons per minute from the Texas Water Development Board groundwater database by well location in this area. He noticed that there seemed to be differences in productivity of the wells between different fault lines. The wells with higher productivity are shown in blue, and the wells that have a lower productivity are shown in red. The following figure shows an interpolated surface of water levels measured during 2020. Again, the color gradient indicates differences in water level readings. Here again, we noticed a correlation with depth to water and possible fault structure. Now looking at this potential fault structure with water level declines, some of the declines seem to be more dramatic in areas between faults. And this slide shows an initial guess at what the direction of groundwater flow may be in this area. In addition to the Middle Trinity Aquifer, also known as the Hensel, there are 3 other aquifers in Bell County. They include the Edwards, the Glen Rose, and the Hostin, which is also called the Lower Trinity. This is where my work begins. We aren't just mapping one aquifer, but all 4 aquifers, along with the aquitards in between the aquifers. Each year as new wells are drilled, we collect the geologic data from drillers' reports and geophysical logs. This figure shows the new data collected in 2020, shown in color by geologic formation, plotted with previously collected data from the prior years. As you can see, there's quite a bit of data here, especially in the Middle Trinity, which has been the focus of our recent efforts. So what do I do with all this data? I first map these data points on the computer in a 3-dimensional workspace, and then assemble all of this data into a 3D geologic model. Before I show you a 3D geologic model, I'd like to take a couple of minutes defining what a 3D geologic model is and is not. While the term 3D geologic model may sound a lot like groundwater availability model, they are not the same thing, although they do share some things in common. As such, I drew a Venn diagram to help explain the similarities and differences. Both types of models have a 3-dimensional structure and can include well locations or other details. The main difference is that a groundwater availability model is a mathematical model. They can be thought of as predictive tools in that their primary purpose is to examine the effect that various future pumping scenarios may have on drawdown. In general, science is much better at telling you about the past than it is about the future. Mathematical models are elaborate formal guesses. There's been a disturbing trend in recent years to describe their output with words like data, result, or outcome. They are nothing of the sort. They are predictions which must be tested against the evidence. A 3D geologic model, in contrast, is not meant to predict the future so much as it is meant to be a mapping tool. which describes the present in some degree of detail with some degree of certainty. So according to Wikipedia, 3D geologic modeling is the applied science of creating computerized representations of portions of the Earth's crust based on geophysical and geologic observations made on and below the Earth's surface. These models can become more detailed as we learn more about the subsurface. And if anyone has tried to use a GPS system to locate their friend's house in a new subdivision, you may have noticed that maps are not always complete and they do evolve over time. Now I've heard some describe 3D geologic models in the industry as simply 3D visualizations. And I'd like to point out that this isn't quite accurate. 3D visualizations are a tool that can be used to visualize the output of any model, including groundwater availability models. So as an example, the Texas Water Development Board has created 3D visualizations of some of the groundwater availability models and has posted them on their website. This slide shows a screenshot of the structure of the Northern Trinity groundwater availability model, and I've circled the Bell County area in red. And this next slide shows that if you rotate this 3D visualization of the groundwater availability model on its side, you can see the layers plunging toward the Gulf Coast. This type of visualization shows the overall structure of an aquifer and helps communicate the overall thickness and extent of the model, but it does not show the relative thickness of model layers, and it does not show the model output, such as drawdown due to pumping. This visualization does not include any information about what is happening inside the aquifer, but maybe we can change that. To look at the geology and other aquifer features in greater detail and in relation to each other in 3D space, a 3D geologic model may be useful. This model covers Bell County, Texas, and the northwestern part of Williamson County. So one of the amazing features of 3D geologic models is that you can create instantaneous cross-sections across the model to look at the inside. These three white planes here are cross-sections that I've generated from this model, which I will show later in the presentation. But before I get to that, let's look inside the model. In this next series of slides, I'm going to show each model layer one by one so you can see the inside. I've peeled off the first layer, the Austin Chalk Formation here. The second layer, shown in orange, is the Del Rio. The little orange spheres floating in space show the geologic contacts obtained from drillers' reports so you can see the data density of this layer. The rather jagged line across the middle defines the lower boundary of the Balcones Fault Zone. The next layer is the Edwards in light green, as shown with the data density. This is followed by the Walnut Formation, which is not an aquifer. Underneath the Walnut is the Glen Rose Formation in light blue. Again, the geologic contacts are shown as blue spheres. As we go further, peeling back the layers of the model, we see the Hensel, also known as the Middle Trinity Aquifer, shown in purple. You can see that this is the layer where we have the most data because of the interest in this aquifer in this area. This next slide shows the Hensel, or Middle Trinity, with the data removed, so you can see the fault structure a bit more clearly. I used the data from the Middle Trinity to start mapping these faults, but I also considered the data from all the layers above and below the Middle Trinity when creating the vertical faults. It appears that the faults propagate through most of the layers, although they become more apparent in the deeper formations. The largest mapped offset occurs at the edge of the Balcones Fault Zone and is large enough to create a discontinuity of flow from the west side of the county to the east side. The smaller up-dip faulted areas have offsets of around 50 feet, which is close to the thickness of the Middle Trinity in this area. Beneath the Hensel, or Middle Trinity, formation lies the Pearsall Formation. The Pearsall is shown in yellow, and again, data density is shown as dark brown spheres. Beneath the Pearsall is the Hostin Aquifer. So at this point, I made another guess. I guessed that perhaps the measured water levels, or more accurately, the potentiometric surface, might have a consistent slope across the fault block. If the faults acted as flow barriers, then I might expect that the relative height of each potentiometric surface would be different for each fault block. So I plotted the middle Trinity potentiometric surface, interpolating across the fault block, but then asking the computer to stop the interpolation at the edges of the block. In a confined aquifer, such as the middle Trinity, the potentiometric surface is the pressure head. In other words, it is how high the water would rise in an observation well due to the natural pressure of the confined aquifer system. So because the middle Trinity is confined, we are seeing the pressure head plot above the actual geologic formation, as we would expect. This slide shows the data density of water levels collected during the winter of 2020. We chose water levels since in the winter because there is typically less pumping in the winter, and it may be more representative of the true year-to-year declines. Again, the spheres indicate data points, the XYZ coordinates of measured water level elevations. And because of the angle and the scale, it is a bit difficult to see the influence of faults on this water surface in this figure. So to get a better view, a different view, I removed the bottom layers and set the vertical exaggeration to 50 times. This view makes differences between the potentiometric surfaces for each fault block more apparent. I see a big gap between the fault block to the right and the other fault blocks. There isn't a lot of data. In fact, there's one point on the far right surface. But what is notable about this particular point is that it's quite a bit higher than the other water level measurements. Also, it's consistently higher, not only in 2020, but in previous years. So this may be real because of the severe offset of this fault block from the others. There may be no flow across this fault. So does water always flow downhill? This is a question that my professors like to ask new civil engineering students. The answer is no, water does not always flow downhill. It flows from areas of high pressure to areas of low pressure. So if the potentiometric surface or water pressure is higher, we might conclude that water is not flowing down dip in that formation. Of course, I would probably like to see some more data to be sure, but this logic might be applied to any of the fault blocks. For the other fault blocks, there's more data available. There could be connectivity between the fault blocks. However, in heavily pumped areas, inflows may not be fast enough to offset the rate of pumping. I'm guessing that what may be happening in the block toward the front of the model, in the surface that is dipping down toward the center, may be this. The faults themselves could be compartmentalizing flow near the county boundary, contributing to large cones of depression in that area. I've also plotted contour lines across each surface so the direction of groundwater flow would be more apparent. Keep in mind that water flows perpendicularly to the contour lines. So from these maps, it looks like the water is primarily flowing to the north-northeast. However, based on the way the faults are situated and the general direction of flow, it's possible that there is water flowing down into the faults and into different formations below. The relationship between the potentiometric surface and the aquifer formation is best illustrated by a series of cross-sections. I cut 3 cross-sections across the model area. Cross-section A is just over the county line in northwest Williamson County. Cross-section B is cut along the county line of Bell County, and cross-section C is a little bit further in. In addition to the geologic formations, I've plotted 3 different water surfaces from the middle Trinity aquifer at different points in time. The light blue line is the water surface, plotted by fault block for the year 2010. The dark blue line is 2020. The red dot is the desired future condition. The desired future condition in the middle Trinity aquifer is defined as 145 feet of drawdown by 2080. And please keep in mind that this is a countywide average. What I did for the purposes of comparison was to plot 145 feet of drawdown in each particular fault block relative to the 2010 surface. In cross-section A, which cuts across northern Williamson County, we see some dramatic drawdowns, particularly in the faulted Balcones fault zone area. This next slide shows a closer view of these water levels by fault block. A suggestion for how I might interpret these water levels is if they are close together between two adjacent fault blocks, there is a potential for hydraulic communication, but if there's a large separation between the two blocks, they are less likely to communicate because there may be a larger pressure gradient to overcome. Also, I might like to see where the most drawdown has occurred. If different fault blocks are decreasing at different rates, that might also be evidence that they are compartmentalized. The second cross-section is right across the Bell County boundary. This is where we see the most dramatic drawdowns, in the heavily faulted area. In fact, some of the 2020 water levels are very close to the desired future conditions set for 2080. These cross-sections indicate that this particular part of the aquifer is highly vulnerable based on the geologic structure as well as pumping influences. And this is a close-up of that same cross-section. As we move farther north into Bell County on this third cross-section, we see things improve a bit. The drawdowns aren't quite so dramatic, and there's more room to go before we meet the DFC. I think it's important to note again at this point that the desired future condition is meant to be a county-wide average. Some areas of the aquifer are quite thin, somewhat isolated, and therefore vulnerable to overuse. These findings would support the creation of at least one new management zone based on the localized aquifer conditions. And here's the cross-section close-up of C. In summary, our general findings indicate that most of the possible faults that we are mapping in the southwest Bell County area show an offset between 30 and 80 feet, with 50 feet offset being quite typical. These offsets are close to the total thickness of the middle Trinity in some areas. Although the water level data is somewhat limited, it does indicate some compartmentalization between the faults. The geometry of the water surface in relation to the geometry of the fault blocks also indicate potential for not only cross-formational flow, but vertical flow between the aquifer units in Bell County. As an idea for future work, I would like to further examine the potentiometric surfaces of each aquifer unit in order to understand how the different aquifers may be interacting with each other. In addition to water level data, water chemistry data would also be interesting. Aquifers that communicate with each other tend to have common water chemistry constituents. In conclusion, I hope that I have presented some good science today, and that my guesses and the guesses that my colleagues and I have made will continue to be tested, both by myself and by others moving into the future. Although concerns about water seem to have taken a back seat lately, those of us in the water industry are all too aware that having a readily available supply of water is the foundation of civilization. From my perspective, water science is always exciting and sometimes controversial. Going back to Mr. Ridley of the Wall Street Journal, Mr. Ridley writes, "So how should we begin to make sense of the flurry of sometimes contradictory scientific views? The only way to be absolutely sure that one scientific pronouncement is reliable and another is not is to examine the evidence for yourself. Relying on the reputation of the scientist or the reporter reporting it is the way that many of us go, and it's better than nothing, but it is not infallible. If in doubt, he reminds us to do our homework, and I think that is sound advice." Thank you very much for your attention.
Any questions for Michelle?
Yes.
Yeah, Michelle, on that last cross-section, especially some of those fault blocks, there seems to be some thickness variations of the units. Do you think that's some sort of lithological basis changes, or have an explanation for that?
My best guess is that it's data limitations. Because I'm using real-world data, it's not always perfect. And so when the computer is interpolating across these areas and there's not enough data control, we'll see variations. If you're drawing a cross-section by hand, you can make those adjustments. But when the computer's doing it, you have to keep that in mind, that there's going to be some irregularities because there are irregularities in the data.